What's up, guys? Happy Wednesday. Hope you're enjoying your day where you get to sleep in and do whatever kind of you want. But remember that you still have work posted. And we do have a test tomorrow in this class. I know, I'm stupid. I suck. I'm the worst teacher ever. Let's get over it. All right. But I want to give you all the answers and I'll go over the study guide so that you are well equipped for tomorrow because guess what? I'm letting you use this on the test. What? Yeah, I know. I'm pretty cool. So just a reminder, tomorrow is the red cohort. Thursday, you guys come in. You're going to be working on this. The other guys, the white cohort, the remote kids, you're going to be just having another day of studying. So just keep that in mind. When you come in on Friday, the white cohort is going to take it. And the remote kids will also take it then as well. All right. So I don't want to take up too much of your time. So let's just go ahead and dive into it. I'll explain each of these. You could forward through the video if you already know some of these. But I just want to go over everything so that you know what to expect and what's fair game for the test. So what is matter? We've talked about matter. This whole idea of matter is kind of underpinning the whole idea of chemistry, the foundation of chemistry. So we are getting into matter, and matter is just anything that has mass. Why isn't this working? I'm going to lose my marbles. There we go. Anything that has mass. So anything that has mass. Well, what's mass? Well, mass is essentially stuff, okay? So I'll kind of say if you put stuff, I would accept that. Why? Because stuff, mass is just anything that is tangible, anything that you could feel, touch. So even air. Why? Because you could feel air. What's that called? Wind. So anything that actually has matter to it or mass or stuff, that is considered matter. All right, the whole universe, for the most part, has some sort of matter around it. Now, space doesn't. If you just have if you're looking at space, there's nothing in space, but there are stars that are obviously mass and things like that. But there are areas that are not matter. So, like for example, what are three things that are not considered matter? A lot of people say space. Okay, well, keep in mind that's the space where there's nothing. All right, so like obviously there's stars in space, planets in space, but the space part of space where there's nothing, and then anything not considered matter, things like ideas. All right, so ideas, abstract concepts like colors. You're like, oh, I could touch red. I mean, my book is red. Well, you're touching your book. You're not really touching the color. So colors, numbers, and emotions, all of those are considered non-matter. Why? Because they're not physical. They don't have mass. They're abstract. Okay, so keep that in mind. Three examples of elements. Well, the periodic table has all the elements you would ever need, and you're allowed to use this on a test or quiz all the time. So all of these are pure elements. Okay, these are pure substances. They can't be broken down further. So this is where you get your stuff like oxygen and chlorine and iron and nickel and copper. All right, so any of these would be considered elements. So give three examples of elements. You could do iron, you do oxygen, and we'll just do hydrogen. So those would be three examples. You can pick any three from the periodic table. And then what is a compound? A compound is elements that are bonded together. So elements, we'll say two or more elements that are bonded, not mixed, bonded together. So a dead giveaway is when I give you the chemical formula. So like H2O, that is a compound. How do I know? Because I give you this chemical formula, and what that's telling me is that there are two hydrogen bonded to one oxygen. All right, so that's what a chemical formula tells you. It tells you what atoms are kind of bonded together. So any example of a compound, or like CO2 would be one. Table salt is sodium, which is Na, and chlorine, which is Cl. So those are all examples of compounds. It's when elements, two or more elements, are bonded together. So that would be a compound. All right, and then down here it says sugar has a chemical formula of C6H12O6. All right, that's true. How many carbon atoms are in one molecule of sugar? So this whole thing is one molecule, C6H12O6. That's one molecule of sugar. How many carbon atoms are in one molecule? It's that number to the right of the element that tells you how many of that element you have in that molecule. So C6, I would have 6 carbon. Well, H12, I would have 12 hydrogen, and O6, I would have 6 oxygen. The number that comes after, that's really small down below, it's not an exponent, it's not up above, it's down below, it tells you how many of that element you have in that molecule. All right? Give 3 examples of homogeneous mixtures. Remember, homo, that prefix means same. So homo means same, and it's got to be the same throughout. So the way I imagine is if you take a handful of this substance and then another handful, would they be the same? And if it is, then it's a homogeneous mixture. My voice cracked. Homogeneous mixture. So what's a homogeneous mixture? Something that is very, very thoroughly mixed. So something like Kool-Aid. If you mix Kool-Aid together, that is going to be a homogeneous mixture because your first sip should be the same as your last sip, theoretically. Another homogeneous mixture, any type of alloy. So we really not touched too much on alloys, but something like steel. Steel is a mixture of carbon and iron that is kind of melted together. All right, so mixtures such as steel, and then really anything that is going to be the same throughout. So Kool-Aid, steel, and I would even say air. Air is a mixture of gases, a bunch of gases, and the air on this side of the room is pretty much the same as the air on that side of the room. Now, you could make an argument that not all air is the same, and that's very true. You go to different parts of the world, the air quality is going to be very different. So, but in a broad sense, if we're talking locally, air is going to be the same. But you can make an argument for heterogeneous as well. All right, give 3 examples of hetero. So hetero means different. That's what that prefix means. So something that's not the same throughout. So Chex Mix. You get one handful of Chex Mix. One would be, one handful might have 5 pretzels. The other might have 2. So it's going to be different throughout. Skittles. Skittles would be different because you might get like 5 orange and 2 red. You know what I'm saying? So that could change, and then really anything that has some separation to it. So here I would say like when you buy store-bought like chocolate milk, so like Nesquik before you shake it, you know what I'm saying? Because all that is settled at the bottom before you shake. Because then you have to shake it up, and then it becomes a homogeneous mixture because then it's the same throughout, but then it settles again. So stuff like that. Anything that has separation, like salad dressing, Chex Mix, Skittles, any of that would be a heterogeneous mixture because it's different throughout. All right? Why is Kool-Aid considered a mixture? Well, why is Kool-Aid not a compound? Let's think about what Kool-Aid is. Kool-Aid is water, which is H2O, and pretty much sugar. Okay? Sugar. So that's C6H12O6. So why is it not a compound? Well, it's because we have 2 different compounds that we mixed together. So water is a compound and sugar is a compound, but what do you do with them? When you make Kool-Aid, you mix them. So that's why it's considered a mixture, is because you mixed several compounds together. These aren't chemically bonded together, they are mixed together. Okay, so that's the difference. Kool-Aid is when you mix it together. Also, you could separate it really easily. How do you separate Kool-Aid? Well, you just let it sit there and evaporate, and then eventually you'll be left with a powder. So I don't know who would do that, but if you're that desperate to get your powder back, I guess you would. All right, describe 4 physical properties of a diamond. So physical properties, anything that you can observe. So if I'm looking at a diamond, let me draw a diamond. And we talk about diamonds all the time, like Sakura. One day her body is going to decay, and then eventually over time she's going to become a diamond, kind of like this, right? And then someone's going to wear her on their ring. So that is a diamond. And what things can you observe about a diamond? Well, it's transparent. Transparent because it's clear, you can see through it. It's hard. It's got a hardness of 10 on the Mohs hardness scale. It's shiny. You can look at its luster. What else? It's I hope that you don't taste or smell a diamond. That'd be bad. But you could put that it's tasteless. If you put tasteless, I'll question you because that tells me that you tasted diamond before. But literally any of these that you could put down for the physical properties of a diamond. So all those are fair game. Just anything that you can observe about it physically. All right. What is mass? All right. Mass. This kind of goes back to when we talked about matter at the very start. So mass is the amount of stuff in something. So I'll just say amount of stuff. And I say stuff very loosely, but I think it's the best way to kind of explain it to you guys. The amount of stuff in something. The technical way to talk about mass is the amount of matter, but when we talk about matter, it's essentially stuff anyway. So amount of stuff in something, that's what mass is. And what's the unit for mass? In science, we used grams. We used grams or kilograms. Remember, kilo is just a prefix. It's still in grams. but kilo is just a prefix. So grams or kilograms is the unit for mass. And then volume. What is volume? So volume is the amount of space that something takes up. So amount of space something takes up. And you may be asking, are those the same? Is that the same as mass? And that'd be no. Something takes up. No, because think about a soccer ball and a bowling ball. All right, they take about the same amount of space. They're about the same size, but one has way more stuff than the other. A soccer ball is full of air. There's not a lot of stuff in it. Okay, air is very spread out, whereas a bowling ball is very dense. It's got a lot of stuff packed into it. So if you're looking at a bowling ball versus soccer ball, a soccer ball is going to have less mass but the same volume. All right, and then what's the unit for volume? Typically, we measure volume in liters or milliliters. Okay, so liters is what we use typically for our units here in this class. So I'll accept both of those. And then what is density? What is density? All right, density is how compact something is. How compact something is. And that is related to volume and mass. How so? As volume increases, density does what? Increases or decreases? Well, think about it. Volume is the amount of space that something takes up. If you got a certain amount of matter and you decrease the space it takes up, all right, you squish it together, you're decreasing its volume, right? If you squish it, if you compress it, you're decreasing its volume. So if you're doing that, does it become more compact or less compact? It becomes more compact, it becomes more dense. So if you increase the volume, if you increase the space that it takes up, if you give it more room, does it become more compact or less compact? It becomes less compact because you're giving it more room, all right? It's able to spread out more. It's less dense. So as volume increases, another way of saying that is as you give it more room to spread out, density decreases because it becomes less compact. If you give it more room, it can spread out, it's less compact, it's less dense. As mass increases though, as you add stuff to it, if you're packing something, you pack your pillowcase, you're going to your friends, if you keep packing that thing with your toothbrush and I don't know, your Tamagotchi, you know what I'm saying? It's going to increase the mass. You're able to fill it with stuff. So as mass increases, density increases because you're packing that thing full, it becomes more compact. So that's how density is related to volume and mass. And then density has the units of grams / milliliters. What does that mean? All right. This is really, really key. If I'm saying that water, actually I'm going to answer this question too. Water has a density of 1 gram. Okay, that's what that stands for. 1 gram per, that slash means per, milliliter. What that's saying is that in every milliliter of water that I have, if I were to measure out a milliliter of water, it's going to weigh on a scale 1 gram. All right? That's what this tells me. This unit, this grams per milliliter, tells me a ratio. For every milliliter of that substance I have, it's going to weigh this amount of grams. Well, the density of water is 1 gram per milliliter. That's kind of like saying, okay, how fast you're going. I'm going 20 miles per hour. Well, if you're going 20 miles per hour, what is that telling you? It tells you that in every hour, you're going to go 20 miles. That's how fast you're going. Every hour that goes by, you're going to go 20 miles. Every milliliter of water that I have, it's going to have a mass of 1 gram. So that's what a ratio unit is. Density has a ratio unit, okay? It's tied to mass, which is grams, and volume, which is milliliters. So it tells you what's its mass per volume, essentially. All right, so the density of water with units is 1 gram per milliliter. Makes it really easy to remember. So copper has a density of 8.92 gram per milliliter. Will it sink or float in water? All right, so let's compare its density to water's. 8.92 versus 1. Which one is higher? Copper's is. So if copper is more dense, it has a greater density than water, what would you expect it to do, sink or float? You would expect it to sink. If it's got a denser, if it's more dense than water, it's going to sink to the bottom. On the contrary, oak has a density of 0.71 gram per milliliter. Well, let's sink or float in water. It's going to float. All right. You throw a block of oak in the water, it's going to float to the top because it is less dense. It has a density that is less than 1 or less than that of water. So it's going to float. So an object's density has to do with if it's going to float in water or not. So that's how you know if it's greater than or less than 1. All right, what's the difference between a physical change and a chemical change? Good question. So physical change and chemical change. Well, a physical change, that would be something like cutting hair. Actually, that's the example down here. So cutting hair. We'll talk about that one. We'll talk about ripping paper. And we'll talk about phase changes. All of those are physical changes. All right, so if you cut hair, what makes that a physical change? The hair itself doesn't change. So that's when the substance, the chemical substance, does not change. Not change. Okay, does not change. So for example, if you cut hair, is it still hair? Yeah. Okay, it's just not on your head anymore. If you rip a piece of paper, is it still paper? Yeah. Okay, it's just 2 pieces of paper now. If you boil water, is it still water? Yes, it's just in a different state of matter now, okay? If you freeze water, is it still water? Yes, it's just, oh no, it's just water, it's just ice now, okay? So 3 examples of physical changes. Anything that doesn't change the actual chemical substance is going to be a physical change, as opposed to a chemical change. A chemical change is going to be something like burning toast. Actually, I'll do the examples somewhere else. But a chemical change, substance does change. Okay, substance does change. So, how do I scroll? Where's my thing? Okay, I'll come back to 24. Give 3 examples of chemical changes. So, burning toast. Because let me ask you this. If you have a piece of bread and then you put it in the toaster and you leave it in there for an hour and then you come back, is it still bread? No, okay? It's going to be this charred piece of disgusting stuff, and you better eat it anyway. All right, so burning toast. That's an example of a chemical change. We talked about the Statue of Liberty. The Statue of Liberty. When France gave us the Statue of Liberty, it was like pure copper, right? But over time, it reacted with the oxygen in the air and turned green. That's a chemical change. It's no longer copper on the outside. It's some new substance. All right, that's actually copper oxide. That's what makes it turn green. So Statue of Liberty changed, the outside of it changed its composition. That actually changed. The substance changed. You're not able to get that back. And then how about your metabolism? So when you eat a galley boy, all right, and you know what I'm saying, like 12 hours later, you see it again, it's not the same. You know what I'm saying? Okay? It's not a galley boy anymore. So something happens and it went through your body and it converted that mass to energy. All right? So it converts that mass to energy. And so it's not the same anymore. If you want to argue that a galley boy is the same coming in as it is going out, then, you know, I might agree to some extent, but also not at all. All right. So that's chemical changes. But going back here, I forgot that this was a problem. List the 6 phase changes and give an example of each. All right. So let me do this. Let me do solid, liquid, and gas. All right. So a solid to a liquid. What's that called when you go from a solid to a liquid? Well, that's just melting, okay? That's melting, all right? Anytime a solid goes to a liquid, so like ice to a liquid, that's melting, all right? Liquid to a gas, that is evaporation. Evaporation, all right? So when you have a liquid like water, you boil it, comes a gas, that's called evaporation. All right, so we're pretty good on those. What about a gas to a liquid? Let's go backwards here. That would be condensation. Condensation. So when you're in the shower and you have the steam coming off the shower, and then you come out of the shower and you look in the mirror and there's liquid droplets on the mirror, that's because the gas hit the cool mirror and condensed into a liquid form. All right. Liquid to solid, what's that? When you have water and then it turns to ice, that's freezing. And then solid, so these are the easy ones, okay? Melting, evaporation, freezing, condensation, those are all the easy ones, all right? Gas to a solid, though. That's one that we're not familiar with. Gas to a solid. Gas to a solid. I'm running out of room here. Let me do this. Boop. Gas to a solid. What's an example of that? Frost. All right, so frost. You go outside in the winter, or actually we're getting to that time now. That time now when you walk outside some mornings, there's going to be a layer of ice on the grass. When that happens, what's happening is the water vapor from the air cools and hits the freezing grass and immediately becomes ice. That's called deposition. Deposition. All right, when frost forms, that's the water vapor from the air becoming a solid immediately. That's depositing onto the grass. So frost is an example of deposition. And then the other one is a solid to a gas. And what is that? For example, dry ice. Dry ice, have you ever seen dry ice? It's this solid block. It looks like ice, and then it's like steaming. It's like what's going on right now. That's an example of sublimation. Okay, so sublimation. Okay, that's a solid going directly to a gas. Is like dry ice. So I gave an example for each of these. I'm not going to write them down, but you can rewind if you want to. So make sure you know these. I know you know the most basic ones, but deposition, sublimation, make sure you know what those mean. All right. All right. So these are the math problems. And remember, I give you each of these equations, so you don't have to memorize them. A cube has a volume of 30 milliliters and a mass of 40 grams. Calculate its density. All right. So I have volume. Volume equals 30. And mass equals 40. All right, so I have that. Calculate its density. I don't know what density is. Well, it gives me the equation density equals mass divided by volume. That's what it gives me right here. So all I got to do now is plug in my numbers. All right, if I plug in my numbers, my mass is 40 and my volume is 30. Okay, 40 divided by 30. You do that in your calculator, you should get 1.33. Okay, repeating, but 1.33. Am I done though? No. Okay, I need to have a unit to it. What's my unit for density? Well, as you remember from above, my unit for density is going to be grams per milliliter. What does this tell me? That tells me for every milliliter of this cube that I have, it's going to weigh on a scale 1.33 grams. That's what this ratio tells me. Okay. It's going to weigh 1.33 grams for every or per every milliliter. So this is my answer. All right, the next one, it gives me the density. It says a cube of aluminum has a density of 4 grams per milliliter and a volume of 20 milliliters. Calculate its mass. All right, I'm trying to find mass. Luckily, it gives me the equation, so I'm going to use that. So I'm going to write down my density is 4 grams per milliliter. My volume is 20 milliliters. So I want to find mass. Mass equals density times volume. So now I just plug in my numbers. Well, what's my density? My density is 4. What's my volume? It's 20. And you multiply 4 times 20, you get what? You get 80, okay? Am I done? No! 80 what? 80 fish? No! Okay, calculate its mass. Its mass is going to be, what's the unit for mass? Grams, baby. Okay, we measure it in grams. How do I know it's not kilograms? Well, if you really want to look back at your density unit, it was grams in the density unit, so you know that you're going to be using grams as your unit here. Okay. For those of you math nerds, you can recognize, okay, something's going to cancel out here. Why isn't this working? I'm going to lose my marbles. Let's see if this works. Boom. Boom, it worked. Okay. This milliliter is going to cancel out this milliliter. And so what are you left with? You're left with grams. All right. And then lastly, a sphere has a mass of 20 grams and a density of 5 grams per milliliter. Calculate its volume. All right, what does it give me? It gives me mass is 20 grams. My density is 5 grams per milliliter. And I want to find volume. Volume gives me is mass divided by density. And now I just plug in my numbers. Well, what's my mass? My mass is 20. What's my density? My density is 5. 20 divided by 5 is 4. What's my unit, though? It's volume. We're talking volume. Is it grams? No. Is it grams per milliliter? No. It's just milliliter, okay? The unit for volume is milliliter in this case. How do I know it's milliliter and not liter? Go back and look at your density unit. Which one is it in the ratio? It's milliliter, okay? Up, beep, boop. Bop, bitty bop. Okay, 4 milliliters is your answer. All right. And last page. This is kind of a little bit different than you online people. I had to modify it because this is more so. This is the paper copy where you actually had to draw something. But for the it's the same concept. On a hot day, Martha makes a glass of lemonade. She has lots of ice so that it's extra cold. A few minutes pass and she picks up her drink. She notices that her hand is now wet from picking up the outside of the glass. All right. Label the state of matter before and after and the phase change. Draw what particles will look like in each state. Wow, what a tough question, Mr. Cully. That's a lot to do. I'm not sure I like you anymore. Okay, fair enough. So what's happening here? Okay, she's got this glass of lemonade. There's lots of ice in it. All right, and let's say it's a hot day. She sets it outside, and then it's gonna have like these droplets on the outside of the glass. You notice that the outside of the glass is wet. Well, what's happening? What causes that? Well, there's water vapor in the air, right? When that gas, that water vapor, which is a gas, touches the cold glass, what does it do? It condenses, all right? It goes from that gas to a liquid. That's why you see droplets form on the outside of a glass. It hits that cold glass, the molecules slow down, and they go into a liquid phase. So what's happening? What state of matter do you start with? Well, the water vapor in the air is gas, and it goes to a liquid. You notice that it's wet on the outside of the glass. So you got the water vapor from the air condensing onto the glass. So that's gas to a liquid, and that phase change is condensing. Condensation. I'll just put condensing. All right. So I went from a gas to a liquid. What's that called? That's called condensation or condensing. All right. So now it says draw what the particles will look like in each state. Well, what do particles look like in the state of matter that is gas? They're very, very spread out. There's not really any order to them. They kind of look like this. And they just want to stay away from each other. They've got a lot of energy. You can even draw some like zoomies, okay? Look at them zooming. Zoom. Look, that one bounced off. Wow, I'm so good. Wow, look at that. That is beautiful, okay? State of matter, that's a gas. Well, what do they look like in a liquid form? They're close together. Not as close as a solid, but they're close together, okay? But they have no order to them, unlike a solid does. So they're not spread apart. They're not bouncing off the walls, but they're able to move around each other. So something like this, okay? That would be an example of the particles. All right, and last question. A worker takes a mixture of cast iron and steel metal and places it inside a furnace that reaches 1500 degrees Celsius. That's hot. The molten cast iron is poured into a mold. The mold is hung out to dry. Later, the worker removes a cast iron skillet from the mold. All right, so let's think about what's going on here. How do we make cast iron skillets? Essentially, what you got to do is you got to take this metal. In this case, it's iron and steel metal, and he's placing it inside a furnace. Well, if you put it inside a furnace that hot, what's going to happen to that solid metal? It's going to melt, okay? It's going to become molten. That's what molten means. It's liquid metal, all right? So he's got this solid metal. He puts it into a furnace and it melts. And now it's a liquid. And then what happens? The mold is hung out to dry. Later, the worker removes a cast iron skillet from the mold. Well, if he removes a skillet, is that skillet still molten? I sure hope not, okay? It's a solid again. So it went from a solid, then he melted them and he fused them together, and then he cooled them off and it became a solid again. So let's think about what's happening here. What did it start as? It started as solid metal. Okay. He takes a mixture of cast iron and steel metal and places it inside a furnace. Then what happens? It melts and it becomes a liquid. All right. Melts and becomes a liquid. All right. And then what happens? After it is poured into the mold, then is hung out to dry. Later, the worker removes the cast iron skillet, so it becomes a solid again. Well, what phase change is it from a liquid to a solid? Freezing. Okay? You could say freezing. We associate freezing with cold. We associate freezing with water. That's not always the case. All right? For this example, freezing would also be when when a liquid metal goes into a solid. You can even put solidification, but I don't think you want to do that. But freezing, all right? When a liquid goes to solid, that's freezing. There's different freezing points for different substances. So don't always assume that freezing means what we think freezing is, because it's all relative to when something goes from a liquid to a solid. So we got melting and we got freezing. So what do these particle diagrams look like? A solid is going to have some sort of structure to them. So I'm going to kind of draw this a little bit neater than I draw my liquid. Okay. So it's going to have some sort of nice structure to them. I'm doing my best. Okay. Look at that. Look at that. That looks nice. Thornberry. Okay. That's a nice, you see these diagonals? Oh yeah, that's orderly. But then a liquid, you got like no order, you know what I'm saying? Okay. Make that look like crap. Yeah. There's no order to that. Okay. And you can even put a little bit of zoomies, maybe not a lot of zoomies, but just to kind of show that they're able to move around each other. Unlike in a solid, they just kind of sit there and they shake. All right, and then back to a solid. So am I able to just, copy? Okay, please just let me copy this. I don't want to do it again. Okay, I have to do it again. All right, so, oh, wait, no. Oh. Watch this, guys. Yeah, that's right. I did that twice. Okay. So a solid to a liquid to a solid. All right. And so solid to liquid, that's melting. A liquid to solid, that's freezing. Okay. So that is the study guide. If you have any questions at all, if you need clarification on anything, then please reach out to me tonight or tomorrow before you take your test. And then we'll get things settled out. But pretty much this covers the main concepts on it. It's not going to look, the test won't look exactly like the study guide because, that would be stupid of me. But just understand what concepts that we've been talking about, and I think you're going to be okay. So again, reach out to me if you have any questions. I'll be on during your period today, during Wednesday, but I can help you other times as well. So let me know if you need help, and have a wonderful day.